Good yourself. Good. Okay, we're going to continue on here. So we're into chapter 9, and in chapter 9 we talked really about phases and water and some properties and intermolecular forces, I believe. So we talked about, the processes of really all those changes of state, melting, freezing, which again happen together at the same temperature, and that's the normal melting or freezing point of a substance, evaporation and condensation, which also again happens at the same temperature, which is the normal boiling point of a substance, and sublimation and deposition, which again also happens at the same time. Remember that in terms of energy, as we go really melting, evaporating, and also sublimation, those are all endothermic processes, which require heat and energy to be put in. As we go the other way around, kind of from when we freeze something, or we go through condensation, or even through deposition, those are exothermic processes where heat and energy has to be released. We talked about at the very end there the idea of delta H of fusion, which is the energy required to do nothing more than change the substance from solid to liquid or liquid back to solid. There's also delta H of vaporization, which is the energy required to take something from liquid to gas or gas back to liquid. Once again, we're not changing temperature here. We're just changing the phase. The substance is in equilibrium as we do that. So at 0 degrees Celsius, for example, for water, you have like ice crystals present. So you have solid and you have liquid happening at the same time. And the same thing as you go from liquid to gas at 100 degrees. You have really both phases happening. Not until you get above or below those temperatures that you really do sort of transition into the next phase. So continuing on in this chapter here, we're going to talk about phase diagrams and how to look at phase diagrams and what we see on them. And phase diagrams are a diagram that basically shows the 3 states of matter, which is our solid, liquid, and gas, and our 6 inner conversions among them. So again, this will show our solid, our liquid, and our gas. And our 6 kind of conversions between them is what we just talked about there, so I won't write it again. These are our 6 conversions between the different states: our melting, our freezing, our evaporation, our condensation, sublimation, and deposition that occurs. What we see with it is the temperature pressure conditions that are necessary for things to again change states or to figure out what state they would be in under those conditions. We'll see some diagrams here in just a second, but when we look at them, we will see one that is referred to as the triple point, and there is a temperature pressure relationship for substances where at that particular temperature pressure combination, you pretty much have all 3 phases happening at once. So you have solid, liquid, and gas basically occurring at the same time. Water has an unusual melting point line. It has kind of a negative slope, which is unusual for a lot of substances, and that accounts for the fact that ice is less dense than liquid water, again, because as it comes together in the solid phase, creates a lot of open space between the different water molecules and decreases the volume, increases the volume and decreases the density in that case. So when we look at these diagrams here, we will also see a part what is referred to as the critical temperature. And at the critical temperature, that's the temperature where there's really no distinction between liquid and vapor phases. So that's the particular temperature, and also goes with the critical pressure. And that point on the graph is sometimes referred to as the critical point, which is the critical temperature and pressure combination, where you have really no distinction between those 2 phases. So things just kind of blur into kind of both phases at that point. And in that point is where we find what is sometimes referred to as a supercritical fluid. And that's one where we have something, because it's sort of flowing between the 2 phases, It has the density of a liquid, but it'll have properties similar to a gas in that sort of temperature pressure sort of relationship. We'll see usually on these graphs kind of a point where that's the critical point. Bless you. And then kind of above that is where we're talking about here, sort of that supercritical fluid where, again, it kind of flows into both phases. So let's take a look at a generic sort of phase diagram. And this is a generic phase diagram. And these are usually the spots that you should know. So usually on the far left here is our solid state. So all this area here is solid. Then we have liquid in this area. And then usually gas is over here. We have pressure and temperature. And we have this line right here. This is our melting point curve, for example. And that is where melting and freezing occurs across that line, right? If we melt, we're going from solid to liquid. If we freeze, we're going from liquid to solid. So you can figure out sort of the pressure temperature combination as to where that would be. If you fall right on that point, and that would be our melting point and freezing point, if it is at standard pressure, and standard pressure is 1 atmosphere. So that's at 1 atmosphere. As you go across and hit that line, that would be your normal melting point and freezing point temperature, which you could find by just going straight down and figuring out what temperature that would correspond to. As we go from liquid to gas, that's across this line here. That's sort of our boiling point line, if you will, and our vapor pressure curve, as is referred to. And again, as you cross over from liquid to gas, that is our evaporation condensation heading the other way. Once again, if you kind of go across that 1 atmosphere, right there on the line would be both phases together happening. And that would be like at the normal boiling point, which once again, if you want to know what temperature that would be, you could just drop the line down and figure out what temperature that would occur for that particular substance. Down here is solid and gas. So as we cross this line here, we're doing the process of sublimation as we go directly from solid to gas. No liquid is passing as we go across that way. And deposition heading in the opposite direction. Again, no liquid being entered as we go across it. And same idea here. If you hit the line, that would be where it will happen. You'll have both phases happening at the same time. Right here, where I have a big circle, is where all of them converge together. And that is the triple point. And at that point, that sort of pressure temperature combination, you have basically all 3 phases occurring at the same time. Up here is our critical point right there. And that's where we find our critical temperature and our critical pressure that we were talking about a second ago. And that is the point where we have, as you can see here, liquid sort of fading into the gas phase or the vapor phase there. And that's where we find our supercritical fluid happening above that temperature pressure combination. Again, no real distinction between the two as it flows over and, kind of have a lot of back and forth sort of happening. So you do need to know the phase diagram. You need to know where you find solid, liquid, and gas on the phase diagram. You need to know where the melting, freezing, boiling, not boiling, evaporation, condensation, sublimation, and deposition occurs, where the triple point is, and where you can find the critical point, which is the temperature and pressure. Any questions on that there? So if we look at one here for our friend carbon dioxide, it looks something like this. And again, we see our 3 phases. We have our solid, our liquid, and our gas. Over here is our critical point at the end of this line. And again, at that point, you got kind of a flow between the two. So in this case, carbon dioxide is dry ice. And if you're familiar with dry ice, it goes directly from solid to gas, right? No liquid cleanup under normal conditions. And that is because normal pressure conditions is 1 atmosphere right there. And if we go across 1 atmosphere, like 25 degrees room temperature-ish, as you can see, my line went directly from solid to gas. It did not hit any type of liquid in that process. And that's why under normal conditions, when we have something like dry ice, it does go directly from solid to the gas phase with no liquid cleanup because you don't have the right sort of pressure temperature combination. If you wanted to force carbon dioxide or dry ice to go into the liquid phase, you would need to do what with the pressure? You got to kick the pressure above 5.1 at least, right? And you also got to kick the temperature above that as well, right? So we would really need to raise the pressure at least fivefold under normal conditions to force dry ice to go through the gas phase. And obviously under our normal conditions, that doesn't happen because we don't have 5 atmospheres of pressure. We're usually around 1-ish. So that's a pretty significant increase in pressure to try to force dry ice to do that. So we can use a curve like this again to determine what phases things are in, what we would expect it to be in based on temperature pressure, or vice versa, figure out, what pressure temperature combination we would need to force something to stay in a particular phase. Any questions on that there? All right, so I want you to take a few moments using this diagram here, which is for carbon dioxide. For each of these, figure out what phase everybody would be in. Is it solid, liquid, gas? Is it a supercritical fluid under each of these conditions? So take a few moments. Okay, so let's take a look at the first one here. We're at 20 degrees, make it a little bigger maybe here. We're at 20 degrees and 72.9. So 72.9 is here. 20 degrees would be somewhere in this ballpark, I would assume. And that means that we should be in the liquid phase at this point. Minus 56 degrees Celsius and 5.1. So minus 56 is right here and 5.1. That is the point where all 3 phases come together, and that would be our triple point in this case, which means we would have solid, liquid, and gas basically happening at this point. We hit 10 and 1 atmosphere. So 1 atmosphere and something like 10 degrees would be in this area. And the label went away, but that should be gas in that region. Looking at minus 78.5 and 1 atmosphere. So that is here in 1 atmosphere. That will put us right on that line. And that is the line between solid and gas, which means since we are at the line there, we would have both phases basically happening at that point. And lastly here, we're at 50 and 80. So 80 is above here, 50 should be out in this region. And that is the region that is past the critical point, and that is where we find our supercritical fluid basically happening at that point. Any questions on any of those there? So once again, you do need to be able to read these, answer questions such as these. Any questions on the phase diagrams? All right. So we'll talk a little bit more about some of the things that we talked about with water. Obviously, water is important for a lot of reactions and stuff that we deal with. Is most of its properties are due to those intermolecular forces, which is hydrogen bonding, which is able to do so because it is a hydrogen bonded to an oxygen. And as we talked about, when it does come together in that ice sort of form, it is actually less dense than liquid water, which is a very unusual sort of situation for a substance because of that hydrogen bonding that's happening. And that's what we see here. This hydrogen bonding with water is a really strong intermolecular force. And it's also really the basis for how it interacts, as we talked about, with other sort of molecules. And again, it's able to interact with other molecules that can also hydrogen bond. So they work really well together to make certain things soluble in it. And also why it does not work well with things that are non-polar, which does not really have a ability to hydrogen bond. It's kind of a neutral bond. So again, they don't have a way to interact really well with one another. Water molecules and ice do expand. Again, they are able to get a lot closer to one another because they really have a little bit more energy in the liquid phase rather than in the solid phase. So even though they're still hydrogen bonding, they're able to, because they have a little bit more energy, actually sort of collapse in on themselves a little bit more in the liquid phase. But with that reduced amount of energy as they go into the ice phase or solid phase, they really end up not, again, being able to get super close to one another. This creates sort of a bloated situation that occurs with water. And again, if we just think about the density equation, that's going to increase the volume overall, and that's going to decrease our density. We know that as well. If you probably maybe put a can of soda or something in the freezer and forgot about it, right? You come back and all of a sudden it has a nice little rounded bottom, right? As it's trying to escape, right? Because those water molecules are now expanding in your like aluminum can that has no more room for it to expand. So it starts to like bloat out the bottom basically of the can as you do that. Science in action. This is good stuff. So all phases of matter usually, again, will expand when it's heated and contract when it's cool. This sort of property of water is really important as well for the idea of how water freezes in things like lakes and those type of situations where maybe we have fishes swimming around on the bottom. So water actually freezes from the top down rather than from the bottom up. If it froze from the bottom up, then there wouldn't be much fish left in those water. And that's because as it starts to freeze, we then get ice that is less dense than liquid water. So it actually floats to the bottom. The warmer, still very cold water, but warmer than the ice there, water will actually sink to the bottom and still stay in the liquid form. And actually that ice that hits the top there actually sort of insulates the bottom water from sort of super freezing, which is really good for this guy here, which is Melvin, by the way. That is Melvin, the fish. Never know where that might show up, like on the next exam, right? Although he does look like he's in an ice cube. He's actually not frozen. It's just really old clip art. So what happens again, as it is freezing, that kind of lower density ice will float to the top. The warmer 4 degrees water, which is sort of the maximum density of water, will sink to the bottom. And again, allows all the fishes to basically be okay. That's why you could also cut a hole in there, which you would never do, obviously, and go ice fishing for Melvin, which would not be a nice thing to do. You should leave him just swimming around, I suppose. All right, any questions on liquids or water there? So we're going to switch a little bit here to finish out this chapter, and we're going to talk about solids and how solids sort of come together. So solids obviously are rigid. They're very hard to change sort of the shape of it. There's a couple of different types of solids. There's crystalline solids, which are really ordered arrangement of particles. And as we'll talk about, they are so ordered that frankly, you could just take a little snippet of the actual way that they come together in the solid form, and you could just keep repeating that unit and you'll have the entire sort of structure back together. That's how ordered it is. So salts, ionic compounds are crystalline solids. Amorphous solids exhibit pretty much none of that. It doesn't have long order or long range order, but does have definite shape and are hard. So things like glass and polymers are more amorphous than, say, crystalline solids. So we're going to look at really crystalline solids here and the crystal lattice and talk about some things. So when it's allowed to cool slowly, particles in the liquid form will again sort of arrange themselves as they go into that solid form to maximize those attractive forces. So as we talked about, no matter what happens, especially if say like in a dipole situation or an ionic situation where you have positive and negative guys come together, there's always going to have to be sort of positives near positives and negative sides near negative sides. But they really do try to move around as much as they can to maximize the opposite attractive forces there, the positive and the negatives coming together. The whole point of that is they will kind of move around to minimize the overall energy that's happening. So the arrangement of these particles in a crystal lattice, our crystal structure is known as a crystal lattice. And if we take something like an ionic compound, they will again sort of really arrange themselves in a way that maximizes that attractive forces. Now we could take a pattern, and that smallest repeatable sort of pattern is what is referred to as a unit cell. So if we had a bunch of, say, atoms here together in the solid form, and we wanted to sort of select a unit cell to help us sort of rebuild this three-dimensional, non-drawn three-dimensional structure there. You may be tempted to think that, if you grab, say, this as your unit cell, that would be really good. We would take this, we have an entire sort of atom there. The problem with sort of grabbing that as your unit cell is there's no frame of reference of where you should put that atom in relationship to the neighbors that are there. So that would not be the best choice to sort of pick for a unit cell. If we grabbed out a unit cell, say something like this, which has a little bit of everybody there, a lot of sort of atoms, and we take this unit cell, which essentially looks something like this. Now what I have is really relationships of how atoms and neighboring atoms are basically in that three-dimensional structure, which means if I just keep repeating that pattern and draw it much better than I just did there, and we put another box over here, you can start to see the whole pattern sort of redevelop, and our whole three-dimensional structure will now redevelop just like it was above there. So a lot of times when we choose a unit cell, we really want to choose something that not only gives us information about a particular atom that may be in there, but also the relationship of how it's sitting next to the other ones. And again, as you see here, you could basically recreate the entire sort of structure. So if we look at this idea there, for example, if they chose that one where we do have a whole atom in the middle and we got a little bit of each of the neighboring atoms, we can very easily figure out, okay, if we just kind of push it back together and keep repeating that pattern, we will get the entire pattern basically repeated. Unit cells are three-dimensional. They usually contain 2 or 3 layers of particles. And again, it's very repeatable that you can, again, rebuild really the whole sort of structure over it. So there's some different types of unit cells. There's cubic, tetragonal, monoclinic, and so forth. We're going to just focus in here on cubic unit cells. Cubic unit cells, all the angles are 90 degrees. So it makes it pretty simple. Also, to figure out the volume of a cube, that is, as we talked about when we did density and all that, is length cubed, right? Is how you get to the volume. Like when you take centimeters times centimeters times centimeters, and that gives you cubic centimeters, right? Length times width times height. So that also makes that calculation quite easier than it needs to be. So let's talk a little about these different types of unit cells and how they sort of come together. Another thing that we talk about is what is referred to as the coordination number. And the coordination number is the number of ions that are basically in contact with each other. So the higher the coordination number, the more interactions you have between neighboring sort of atoms and molecules that may be in there. Packing efficiency, we're not going to get into too much of that, but packing efficiency is how they all could kind of fit together in that solid state in the most efficient manner. And again, the higher the coordination number, the more efficiently the atoms are able to pack together. And that's because if they has a higher coordination number, that means they clearly are close to each other, right? So they're touching each other, so they're able to really pack themselves in, rather than a smaller coordination number where not a lot of guys can really get close to one another. So cubic unit cells, which is the ones we're going to focus in on, have all right angles, 90 degrees. The length of the edges are equal to each other. And when we talk about a unit cell, in the corner of these cubes, you have an eighth of a cell. And since a three-dimensional cube has 8 corners, that means you basically have one whole atom, right? And each in the total of all the corners together. If you happen to slice the unit cell, which slices perhaps an atom in half, you will have a half of a unit cell or a half of a atom there on the face of a unit cell. And if you have something that belongs along the edge of it, you'll have a fourth of an atom. So we're not going to deal too much with spheres, but again, the volume of these cubic unit cells will get us there. Ultimately, we're going to be looking at density of these things a lot of times. So that is sort of how we're going to get to the volume part of the density calculation. Any questions on that there? So these are the three different types of cubic unit cells that we're going to talk about. The first one is a simple cubic, which is sometimes abbreviated as SC for simple cubic. It has one atom per unit cell, which is an important number to remember. So simple cubic has one atom. To calculate the edge length, it is 2 times the radius. And it has about 52% packing with a coordination number of 6, basically. The next type of unit cell, we're going to go through each of these individually in a second, is body-centered cubic, which is sometimes abbreviated as BCC. In a body-centered cubic cell, you have 2 total atoms involved in each unit cell. To calculate the edge length, it is the 4 times the radius divided by the square root of 3. And it has a coordination number of 8. And as you can see, the efficiency of packing goes up because, again, more atoms within contact with each other. Lastly, we have face-centered cubic, which is FCC. That has 4 total atoms involved. And it is actually, I'll bring the R out in the front. It's like 2 times R divided by the square root of 2. It kind of looks like the R at the back end there is underneath the square root, but it's actually not. So it's actually outside the square root there. And again, we have a coordination number of 12. And obviously, you can again see a lot more packing happening there, a lot more interaction between the atoms in each of these. So let's take a look at each of these individually here and see some of the important details of it. So looking at our simple cubic cell, it has 1 total atom. So again, our simple cubic, 1 atom. And that atom is made up of basically an eighth of an atom in each of the corners. So once again, we have 8 corners, also back there. And that gives us our total of 1 atom made up of the eighth of an atom in each one. It is 2 times the radius is the edge length. It has, again, a coordination number of 6, as you could kind of see maybe better here as we web it out here. We do have this sort of eighth of a guy in each of those corners. And again, some interactions happening around there to give us our coordination number that happens. So for simple cubic, you need to know that it has 1 total atom. To calculate the length of this edge, it is 2 times the radius. And again, here's sort of a 3-dimensional cutout of what we got going on. And that's our eighth of an atom again in each of those corners as they come together. The next one is body-centered cubic, which has basically 2 atoms. So this guy has the same eighth of an atom in each of the corners. So that is our 1 total atom there. And body-centered means right there in the dead center. Guess we should circle with blue on blue, I suppose. Let's go with red, maybe. Right here in the center is a whole atom sitting right there in the center of that particular unit cell. So that is our second atom, which gives us 2 atoms overall. To calculate the length there is going to be 4 times the radius divided by the square root there of 3. And again, the coordination number here is going to be 8. And again, you can see we got a lot more interaction because we do have that atom kind of stuck right there in the middle. So there's a lot more contact happening with the parts of the atom on the corners, which gives us, again, a greater packing efficiency and also a little higher coordination number, as you can see in this picture. All right. The last type of one is a face-centered cubic. And face-centered cubic, again, basically we'll have our 4 atoms basically happening there. And that is, again, 1/8 of an atom in each of the corners. So that's going to give us our 1. And basically, if you can see here, we're going to do face-centered, which means we're going to slice this atom on each of the faces in half. So there will be basically a half an atom on each of the faces of our cube. And since there is 1, 2, 3, 4, 5, 6 faces to a cube, so we get a half an atom for 6 faces. That's our other 3 atoms, which is basically on the face of each of that cube. And that gives us a grand total of 4 atoms basically happening here. And that is square root clearly moved. So it's 2 times r, 2 times the radius, times the square root there of 2. Clearly, with those half of atoms on each of the faces here, as you can see here, kind of sliced in half, we have a lot more contact happening on all 6 faces and giving us that greater packing efficiency and the coordination number of 12. All right, so let's take a look at this problem here together, and we will talk about how to do this. So let's calculate the density of aluminum in a face-centered unit cell that has 143 picometers. So pico is 10 to the minus 12 there. So let's talk about how we go about doing this. So the first really important piece of information is it is a face-centered cell. So if we go back there to our pictures here, that was this last one that we just looked at. And this face-centered cell has 4 total atoms. Again, 1 atom from all the corners and the 6 faces that have a half an atom each. And that's really important because overall here we are looking to calculate the density in grams per cubic centimeter, right? So we're going to use the idea that it has 4 atoms to help us get to grams. So if we want to go from atoms to grams, we have to do a couple of things. We want to go from atoms to moles, perhaps, and moles to grams. So that is how we're going to get to the grams part, which is going to be the top part of our density calculation. To go from atoms to moles, we need to use Avogadro's number to do that. And we need to use the molar mass, right, to kind of take it the rest of the way there to get into grams. So how are we going to get the volume part of it, which is the cubic centimeters? Well, we know that, again, that this is face-centered, which means we know to calculate the length of the edge. It is 2 times the radius times the square root of 2. So if we take that into account here, 2 times the radius times the square root of 2, we could use this to get our length. And we have to remember that this length is not the volume, right? So we then would need to go and to figure out the volume, which would be our length cubed. And that would be the bottom part here, which would be our cubic centimeters. So doing those 2 calculations will allow us to really figure out the density here of aluminum in this case. So let's take a look and do this together. We're going to start with the first part, which is there are 4 atoms of aluminum. Using Avogadro's number, there is 6.022 times 10 to the 23 atoms per mole of aluminum. If I stop at that point, my atoms of aluminum cancel. I can then go to the periodic table and find the molar mass of aluminum, which is 2698 grams per mole. The moles of aluminum will cancel, and that will give me the grams of aluminum that there are. So obviously we want to make sure we're using our exponent button here. So 4 times 2698 divided by 6.022 to the 23. Going to give us 1.79 times 10 to the minus 22 grams. And again, that is basically the top number there. Any question on that calculation? So this is why knowing how many atoms there are in, say, a face-centered is important, because it's going to allow you in this particular case to get to how many grams of aluminum that would be. Questions on that calculation? The next thing I want to do is figure out the volume, but I do want to kind of do something before perhaps I just kind of throw this number in here, although that is the radius at 143 picometers. Ultimately, I do want my length to be in centimeters so that when I cube it, I will be in cubic centimeters. Otherwise, if you wait to the end, you got to do some type of conversion at some point. So you might as well just convert it to the right units at the beginning. That way you'll be in the right units at the end. So before I begin sort of the calculation for the length, I'm going to turn my radius into centimeters so that again, at the end, it's in the right units. You do have to do it at some point. So like I said before, why not just do it up front? So we got 143 picometers. 1 picometer is 10 to the minus 12 meters. And in 1 meter, there's 100 centimeters, right? So that's going to convert me over into centimeters. And if I do that, that's a 143 times 10 to the minus 12, or 1 times 10 to the minus 12 times 100. Bless you. Going to give us, find my answer here, going to give us about 1.43 times 10 to the minus 8 centimeters. So really, I didn't do much in terms of working towards the volume here other than just getting it into the right units. So at the end, everything's fine. Now I can put into my specific length calculation that's for a face-centered, bless you. And in this case, we will take 2 times our radius, which I've already converted into centimeters, times the square root of 2. So that's going to give me times 2 times the square root of 2 here. And that is going to give me 4.04 times 10 to the minus 8 centimeters. Once again, that is not my volume, right? That is just the length in centimeters. So to get it to my volume, I'm going to cube it, right? To turn it into my volume. So that'll be like centimeters times centimeters times centimeters. And since all the length are equal in a cubic cell like this, and they're all 90 degrees, we could just do that straight up and cube it. And that gives me a volume here after I cube it of 6.62 times 10 to the minus 23. And because I cubed it, I am now in cubic centimeters, which is a volume. And again, the right units that I need for my density calculation. Any questions on that there? All that's left at this point is, frankly, divide the two numbers. So let's do that. So density here would be our mass, which was 1.79 times 10 to the minus 22 grams, divided by our volume of 6.62 times 10 to the minus 23 cubic centimeters. And if we do all that good stuff there, again, making sure to use your exponent button, that looks like a 2.71 grams per cubic centimeter. That's a lot of numbers to get there. It's that number, but we did get there. So the density here of aluminum here would be 2.71 grams per cubic centimeter. Any questions on any part of that calculation there? So again, knowing the different unit cells and how many atoms, important to get you to that mass component, and obviously knowing the formulas there to figure out the correct length. And really, units are really important just to make sure everybody's in the right units. And I find in these type of problems, it's good to kind of just get them out of the way and do them up front, so you don't have to worry about it down the road. Any questions? All right, I did one. So how about you do one? Let's see. All right, that's aluminum. All right, so why don't you give this one RB crystallizes and body centered. It has an atomic radius of 247.5 picometers. So again, pico there is 10 to the minus 12. RB is where did you go? Something 8547, I think. Okay, so let's take a look. So once again, some differences here. This is body centered, which is what the BCC means. That means it will have a different number of atoms. This is the one where we again have a total atom from the corners, an eighth of an atom in each corner. And body centered means, again, there's one sitting dead center, an entire atom basically in the middle of the cube. So this guy's got two atoms. Also has a different length sort of calculation that is 4 times r divided by the square root of 3. So a couple of different things because this is a different unit cell. But we really will approach it the same way. We really need to end up getting grams, which is going to come from our atoms, and our volume, which is obviously going to come from our radius, which was given to us in picometers. So I'm going to again start with the atoms and kind of roll through the same similar calculation there. 2 atoms. We will need Avogadro's number there to convert it into moles. So Avogadro's number on the bottom. And a mole of RB up on top. That gets rid of atoms. Again, we do want to get it though to grams. So we're going to go one more step here. We want to get rid of moles. So using the molar mass from the periodic table, there's 8547 grams of RB in a mole. Those guys will cancel. So that will get us here 2 times 8547 divided by 6.022 to the 23. Going to get us about 2.84 times 10 to the minus 22 grams. That again is the grams part there for our density calculation. Any questions on that part? Just like on the last one here, I'm going to get myself, so I don't make a mistake later on, into the right units. So we are given it in picometers. So I'm going to do that same sort of conversion to get it into centimeters. That way, when I do eventually cube the length, I will be in the right units. So once again, that conversion, that 10 to the minus 12 means 1 picometer, and one of the prefix units, there's 10 to the minus 12 of the base unit, which is meters in this case. The picometers cancel. We don't want to stop there because we're in meters only. So in 1 meter, there's 100 centimeters. And again, that's going to get me into centimeters. And that's going to get me 247.5 times 10 to the minus 12 and times 100, 2.475 times 10 to the minus 8 centimeters. So now that I have my radius here in the units really I want, I could plug it into my length calculation. And my length in this case is 4 times r divided by the square root of 3. So it's going to be 4 times my 2.475 times 10 to the minus 8 centimeters divided by the square root of 3 in this case. So that will get me 5.72 times 10 to the minus 8 centimeters. Once again, that is only my length and not my volume. So because again, this is a cube, we just cube it basically. So to get our volume, we're going to take the length cubed. So to do that, we will just cube this number here. And if we do that there, we will end up with 1.867 times 10 to the minus 22 cubic centimeters as I cubed it. And that will obviously be the bottom number there that I need. Any questions on that? All right, so the last part here obviously is to finish it. So we will then take both of those numbers into our density. So our grams of 2.475 times 10 to the minus 8 centimeters, which is obviously not my grams, but my centimeters there. Good thing they have erasers, I suppose. Let's try that again. That was 2.84 times 10 to the minus 22 grams, divided by my 2.475 times 10 to the minus 8 centimeters. Again, the units here are not going to cancel out. Keep wanting to put that bottom number in first. So let's try the other number. There you go. We should use the right number as well. That would be good. That would be is the volume number. Take 3. We'll just cut this out later in the video. Here we go. Let's actually take the volume number, which is right there, 1.867 times 10 to the minus 22 cubic centimeters. That looks a little better, I think. 2.84 to the minus 22 divided by 1.867 to the minus 22. There we go. We'll go with 1.52 grams per cubic centimeter in this case. Yeah. Any questions on that there? So these are unit cell type problems, as I mentioned, different types, number of atoms. Variation on this problem would be you're given the density and maybe has to back calculate something like the length of this edge or the radius or something like that. So those sort of variations kind of working backwards in some cases. Any questions on unit cells or anything like that? All right, that wraps up this chapter. We're off to the next one here as soon as I find it, hopefully. Okay, so the next chapter there is solutions, which is chapter 10. There's a number of sort of calculations and stuff in here that we sort of already did previously. So we'll go through them a little bit quicker. And then towards the back end here, some of the new stuff that relates some of those calculations and stuff that we did previously. When we talk about liquids and things being soluble, when two liquids completely mix together, they're sometimes referred to as being miscible with one another. And when we do put two liquids together, the reason that they really will mix is because they really do share similar intermolecular forces, as we talked about, sort of that like dissolves like. So perhaps two things that can hydrogen bond together will mix. And when they do, it will just look like obviously one layer in there. Even if you have two solutions, right, everything will mix, just like sort of a solid dissolving in a liquid. When two liquids really do not mix together, they're said to be immiscible in each other. And in that case, you definitely will see some layering happening, as again, maybe they're using two different types of intermolecular forces. Like if you took some carbon tetrachloride with water, carbon tetrachloride, if we just quickly sketch its Lewis structure, is a symmetrical geometry with everything attached the same, which means it's a nonpolar molecule. And because it's a nonpolar molecule, in terms of intermolecular forces, it's going to want to use dispersion forces. Right? And that's different than water, which obviously is a polar molecule and has the ability to hydrogen bond. And what it's going to want to use is basically that, hydrogen bonding. So again, we have two very different ways in which they want to interact with each other. And that's going to mean that over the long period of time, they're just not going to stay mixed at all. So they are going to separate out. And that again is why we see the different layering that's going to happen, as opposed to if we took something again like methanol and water, because methanol does have this polar bond and water obviously has that as well. They are able to hydrogen bond with each other, so they will definitely mix really well together, and you'll just see that same layer. So that brings up again that same idea as we talked about, like dissolves like. So things that are polar and polar are going to be soluble in each other. Things that are ionic and polar definitely will be soluble in each other. And thing that sometimes, again, people miss is nonpolar and nonpolar are going to be soluble in each other. So if you have two nonpolar liquids, they will definitely be soluble in each other because they are both using dispersion forces. So that will work out really well. And again, there's our different layering that we see when they do not mix. When we have solid substances, for example, in terms of water, Ionic solids are definitely going to be soluble in water. They will use that ion dipole interaction that we talked about in the previous chapter. And that is basically the process of how, again, things dissolve. And just like we talked about there, the water will surround our positive ion as we go to dissolve it with its negative side, and also will surround the negative ion with the positive side of water. So once again, it has no problem with those things. Non-ionic substances like sugar and ethanol, again, are also going to be soluble in water for what I just showed you there a second ago with methanol. They both pretty much have OH groups on them. And that means that they have the ability to hydrogen bond with water, which makes them quite soluble with it. Even sugar, which is a relatively larger type molecule, is still soluble because it can overcome that, because it has a lot of OH groups all over it. So everywhere it has an OH group, it's able to interact with water and makes it quite soluble. So typically speaking, something like ethanol or methanol will also be soluble. Solubility does start to decrease as you build out sort of the nonpolar side of those molecules. So when we look at something like ethanol, looks like this. And once again, this part here is really nonpolar. This part here is polar. So as you build out, say, that part of the molecule, you get to something like heptanol, which is like 7 carbons out that way. The solubility pretty much drops to nothing. So, and that's because the nonpolar part is really too big to allow that little polar part to interact well with water. Sometimes referred to as steric hindrance, it gets in the way basically. So it's too big to interact well with the small water molecules. So solubility really does start to decrease. But if you have some alcohols like ethanol, methanol, propanol, and so forth, they're relatively small, have that OH and ability to hydrogen bond. They're quite soluble in water, but as that bigger nonpolar part gets larger and larger, solubility does sort of stop. And there's methanol, again, hydrogen bonding. They both are able to hydrogen bond because they both have a hydrogen directly attached to an oxygen. So a reminder that in order to hydrogen bond, you need that hydrogen that's directly attached to either nitrogen, oxygen, or fluorine, again, in order to have the ability to hydrogen bond. There's our ethanol, also hydrogen bonding up there. When we have something like oil and water, again, they really don't mix because pretty much oil is nothing more than a super long chain of carbons and hydrogens together, carbons attached to carbons and carbons attached to hydrogens, which are all non-polar bonds. So something like oil definitely is going to try to use dispersion forces, and something again like water is going to use hydrogen bonding. So a very, very different way. In addition, the size really does matter as well. In order to get really anything to sort of work with water, dissolve in water, mix with water, you have to replace water and water interactions with similar size sort of solute interactions. And something like oil is really quite too big to fit nicely in there with all the other waters. So I might have used this example before. You know, if you try to park a regular sized car in a garage, it works okay. But if you try to put like a semi truck in the garage, sort of fits, but not really so well there, right? It's going to definitely hang out. And that's sort of the same idea here. We try to put something like oil, which is just a giant non-polar molecule, not going to work well, has no way to really interact over the long period of time. So they'll just sort of separate out. So again, that idea of like dissolves like, polar, polar good, non-polar, non-polar good, ionic, and polar good, all going to be soluble. And obviously, if you cross over polar and non-polar, not so good, going to be insoluble if you try to mix those guys together. That brings up the idea of hydrophilic and hydrophobic. Hydrophilic is a part of a molecule that really likes water. It's a water-loving part of the molecule. And that's going to be obviously any part of the molecule that's polar, right? Like the OH group that we just saw there. Hydrophobic is the water-hating part of the group or the molecule, and that's going to be like the non-polar region. So like in ethanol, that's going to be this part of it. That's the non-polar hydrophobic part. That is our polar hydrophilic part that works really well with water. This is also how soap sort of works. Again, it has both parts. It has a hydrophilic part, which is the part that does like water, and soap has a hydrophobic part, which doesn't like water, but likes dirt, and that's why it mixes really well with dirt and aligns on the outside the part that likes water, so that when you wash off your soap, the dirt goes with it as it traps it inside. So here, as we mix octane, which is nonpolar, and carbon tetrachloride, which is nonpolar, both going to use dispersion forces. So we're going to get some pretty good mixing. Again, gasoline, which is nonpolar, and water, which is polar. We will get our separations of those two. Although water can use dispersion forces, and really anything can use dispersion forces, the problem is the gasoline cannot maintain those interactions like something like water. Remember that water, which is polar, no matter what you do to it, will always have a positive side and negative side. So it will never change. It's always good to go. Something like gasoline there or oil needs something to occur in terms of dispersion forces to allow it to have that positive negative side and interaction. So it cannot maintain that positive negative side because it ultimately is nonpolar. And that's why it will ultimately fall apart and not be able to sustain the mixing that occurs. So when one substance dissolves in another, it is said to be soluble. And obviously when one does not, it is insoluble. There is a limit to the solubility of one substance in another. Gases are always soluble in each other, and that's because gas molecules are flying around, which means they are constantly mixing with each other as they are flying around in the same container. Some liquids are also usually soluble in each other. And again, that is your polar, nonpolar going to be definitely soluble in each other. The solubility of a solute does depend on temperature. So typically, if you have a larger solubility of a solid in a liquid, if you increase the temperature, because you're doing two things, you're increasing the temperature, which obviously increases the energy. So that's going to allow everybody to kind of dissolve more and be able to kind of take more of that in. When we talk about the solubility of a gas in a liquid at a lower temperature, you have a greater solubility of it. And if you just think about that logically, if you have a liquid and a gas molecule at a lower temperature, as we talked about, our gas molecules should be moving slower, which means it will stay in the liquid part for a much longer period of time than if you had a higher temperature where it's moving a lot faster and it's going to be able to jump out of the liquid a lot quicker. The solubility of gases obviously does depend on pressure. So at a higher pressure, you have a larger solubility of the gas in a liquid. And that is also with the gases and gases. When you have a high pressure, you have a small volume, right? Boyle's law. So that means that my gas molecules are definitely near each other for a lot bigger period of time. And they're going to be mixing because they're all in a very small location. Now, when we talk about ways to describe solutions, there is a limit to how much solute you could get to dissolve in a given amount, or solute you could get dissolve in a given amount of solvent. So simple example is obviously if you take a couple of sugar packets, should dissolve in a glass of water. If you take the Costco size sugar and pour it into your glass of water, at some point it's going to not dissolve. So you don't have enough solvent there to dissolve all of that. So there's two ways we describe a solution. One way is a saturated solution, and a saturated solution is one where basically at that particular temperature, you've hit the maximum amount of solute that will dissolve. So if you try to dissolve any more solute, it will not dissolve. It'll just kind of pile up. A reminder that a solution, right, is made up of a solute and a solvent, right? A solute is the smaller part of the solution, the stuff you typically dissolve. The solvent is the larger part of the solution, right? Like water in a lot of cases. The opposite of that is a unsaturated solution. And in an unsaturated solution, you pretty much have not hit that point yet. So you could take more solid and it will continue to dissolve. It will continue to dissolve until you hit a saturation point or a saturated solution. And at that point, it will no longer dissolve. So unsaturated, you haven't hit the maximum amount that will dissolve. saturated, you're pretty much at that point where if you add any more solid, no more will dissolve, and it basically will just start to pile up. Any questions on that there? Third type of solution is a super saturated solution, which is like a saturated solution, but super, I suppose. But basically how you make a super saturated solution is you actually will make a saturated solution while you're heating it usually. So as I'm heating the solution, that's going to change the solubility. That's going to allow me to dissolve a lot more solid in it, right? Because it's much hotter. So as you heat this thing up, you could dissolve a bunch of solid in there. And then typically what you do is after you get it all dissolved, you take it off the fire and you let it cool down. So at this point, it's still a liquid and you're letting it cool down. What happens to solubility as it starts to cool down? Solubility should then start to decrease, right? Because it increases as you're heating it and it's starting to decrease as you let it cool down. So you let it cool down and it's undisturbed. You definitely don't want to touch it or play with it too much at this point. And you still have a liquid at this point. And what you basically liquid sort of solution. And what you have at this point, once it's cooled down, is you now have way too much solute dissolved in there. For that cooler temperature. But it is still really in liquid form and everything is still dissolved. It actually creates a quite unstable solution. It is so unstable that if you just took like that speck of solid that you could barely see and you like decided to drop just that one little speck in there, what's going to happen is the solution can go, whoa, too much solids dissolved in here. And it will actually go from the liquid state, and what you could actually see is all of the solid will start to basically leach out of the solution, and it will go from a liquid state to basically a rock hard solid at that point as all the solid basically comes out. It actually can happen just by tapping it on the bench by accident. I know that because I demonstrated it not too long ago, and I just took the flask out and put it down and it just started coming out of the solution without me adding anything. So that's how unstable this solution is because you basically force all the solutes, the solid to dissolve in it. You lower the temperature, which means you now have created a situation where that much should not be dissolved in there. So what you do when you add that little kind of crystal is it kind of pushes it over the limit there, and everybody just comes out of solution in that particular case. Any questions on that there? It's a cool experiment. They used to let you do it a lot of times, but then they would have you put your thermometer in the test tube, and then it would come back to a solid, and then you had a thermometer stuck in the test tube like a popsicle. People, it's like, how do I get it out? You know, so it's like, so after they lost a lot of thermometers and test tubes, they don't do these experiments anymore. But here's an example of that. This is our supersaturated solution here. And it's kind of hard to see, but it's basically just dropped like one little drop right about there. And you can see that one little drop is enough to cause the solid. And this is the solid basically coming out of solution. And by the time it gets down here, it's going to be pretty much rock hard, no liquid in that case. Any questions on that there? What's up? Yeah, so a lot of times what will happen is the solid will come out of the liquid, and you basically have this way too much solid in there to begin with. And part of that process as well is, for example, that one we just looked at, if you fill the flask, is super hot. So it's a very exothermic reaction. So you will sort of evaporate off any of the solvent that's sort of there at that point. Some of it will crystallize with the solid as it kind of goes through there, but a lot of it's lost through that process, and also the process where you really were heating it, right? So as you're heating it to dissolve it in, you're losing some of that solvent along the way. So as it then kind of goes to the solid phase, some of that gets carried into the crystals, but a lot of it's also lost through the heat and the process of it happening. Other questions? All right. Okay, so continuing on here, we're going to talk about pressure and the solubility of gases. This is what is sometimes referred to as Henry's law, and it's sometimes referred to also as like the soda can effect there, what happens with soda in a can. Henry's law says that the solubility of a gas in a liquid is proportional to the gas over the solution. Here's a couple of versions of sort of Henry's law. C is our concentration, our molar solubility, which is basically a fancy way of saying molarity, which is moles per liter. K is Henry's constant. So that is a constant value that you would look up in a table based on the gases you're dealing with. And P would be our pressure in this case, right? In each of those cases. So the idea behind Henry's law is this: when you have a soda can, before you pop the top, just before you do that, you basically have a lot more of the CO2 dissolved in the liquid portion, because obviously the can is under a lot of pressure, right, before you pop the top there, although it looks like I did already in my picture. So as we just talked about, what you will have before you open the can of soda is you'll have a lot more of the gas or CO2 dissolved in the liquid portion. Once you do pop the top, you release the pressure goes down, also gives sort of an escape route there for your CO2 to come out of the solution and escape. That's like the fizzing you see, right? When you open your soda can, it kind of fizzes a little bit coming out the top. Is also what happens as the air blows it away. Eventually, if you leave your soda can open for a while, it becomes very flat, right? And that's because all the CO2 has escaped the liquid portion, went through the hole in the opening there, and basically got blown away. And now you have a flat soda, which of course you drink. Why not? How bad could it be? So looking up those values, it is gas specific, the Henry's law constant, which is the K. And again, you would look it up for whichever one that you may be dealing with in this case. So that's what we see here. Again, before we pop the top, a lot more of the CO2 is dissolved there in the liquid portion. And again, we give it sort of an escape route. And also with that less pressure, that's going to allow a lot of those gas molecules basically to escape the liquid part of the portion of this of the solution. So if we look at one here, what is the pressure of CO2 that's required to keep the CO2 concentration at 0.12 molar? We could use Henry's law here to help us calculate that. And again, we will have to look up a couple of things. First off, we would need the constant for CO2, which is 3.4 times 10 to the minus 2 molar over atoms. Over atmospheres is our constant. So our C is equal to K times our pressure. At this case, we have our concentration, which is 0.12 molar. We obviously just looked up our specific Henry's law constant here. That means we could rearrange here and solve for the pressure to figure out what pressure we would need to keep it there. So the pressure in this case would be C divided by K, and that would mean 0.12 molar divided by our 3.2 times 10 to the minus 4 molar over atmospheres. When we divide it out, our molarities are going to cancel, and our atmospheres will end up on top, which would be 0.12 divided by 3.2 to the minus 4. That is going to give me this thing in scientific notation, which is going to give me a pressure here, I think, of 375 atmospheres, which is a pretty high pressure there. Did I get the right number there? I did not. I put on minus 4. I felt like it was a little high there. So that is a 2. I guess that would help to look up the right number. That's some bad memory right there. 3.4 to the minus 2. I only looked at it like 2 slides back. All right, so take 2 here. We'll again cut that out in post-production later here. So that's 3.4 to the minus 2. Let's try that again. All right, 0.12 divided by 3.4 to the minus 2, going to give us 3.5. That feels a little better. Not so super pressure there. There you go. So 3.5 atmospheres would be the pressure that we needed when we look up the right number there. That still is about 3 times, right, or 4 times almost the normal pressure. So again, that's why there's a lot of pressure, obviously, in that soda can before you pop it. Any questions on Henry's law here? All right. Let's see here. Oh, that looks more like what I got the second time around, I guess. All right. So we're going to kind of go through this part a little quick because we just talked about it not too long ago when we did stoichiometry and molarity and all that. So some of these concentration units are important for what we're going to talk about here in a second, which is colligative properties. A reminder, some of these concentration units for solutions, percent by mass, which is percent mass to mass. That again is our mass of our solute over our mass of our solution times 100. So remember, we actually talked about 3 different types of percent concentrations. We had our mass of our solute divided by our mass of our solution times 100%. We also had percent volume to volume, which is the volume of solute divided by the volume of solution times 100%. And there was percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. So we did some examples previously, and they're in this handout as well, of these things, and you could obviously plug and chug into there. A couple of reminders. This first one really is the most important one. You do want to make sure when you get the mass of the solution that, again, it is both the solute and the solvent together. The other ones you don't usually have to worry too much about it, as usually the volume is given to you or something like that as both the solute and the solvent. Also, if you did have a 4.25% by mass solution of calcium chloride, again, what that means is you have 4.25 grams of calcium chloride over 100 grams of solution that you could use as a conversion factor. And you could do a similar sort of conversion for any of those guys. Volume to volume would mean you would have 4.25 milliliters of calcium chloride in 100 milliliters of solution. Mass to volume would mean that you had 4.25 grams of calcium chloride in 100 milliliters of solution. So I think we did some examples where, if you want to take more of a dimensional analysis approach, you could kind of convert that into a usable conversion factor, or you could plug and chug into these equations, and it's really the same math. It's just sort of whichever one you sort of prefer. Question on that there? Yeah. This one here. That's percent mass to volume. It's the mass of the solute over the volume of the solution times 100%. Yep. Other questions? Okay. So we're not going to do this example as we did it previously when we were going through that chapter. So the answer will be the same here. In this case, 4.76%, by the way, I think. This one as well, we did earlier in a previous handout there. Answer is 13.2 grams. See, I remember the answers here. That's pretty good, I imagine, right? We also talked about when we were going through that, and this should be, by the way, at the end of the solution stoichiometry titration handout. It's the last several slides we went through during that time. Molality, we also talked about. Molality, again, not to be confused, obviously, with molarity, which is moles per liter. Molality, again, is moles per kilogram of solvent. And this guy here is definitely used a lot in colligative properties that we're going to talk about here in a second. And again, it's moles of solute divided by kilograms of solvent. And again, not to be confused with molarity, which is moles of solute per liter of solution. And that is capital M, and this guy is lowercase m when we do it, moles per kilogram. Again, a reminder that sort of the density is usually the thing that sort of ties those two together. If you need to kind of go from one to the other, the density is sort of what is used to kind of do that. So molality is used a lot in colligative properties and a lot of the calculations, and we'll do some in just a bit here. So again, we're not going to do this one either, since we did it previously. And obviously our mole fraction, which we did at that point, we also did it in gases, and hopefully you did it on the exam that you just got back, right? So mole fraction is also used in some of the colligative property sort of calculation, and that is basically the moles you're interested in over the total moles, right? is how you get the mole fraction, which is what X stands for. It's basically a fraction here. It's not going to be a percentage, so we do not multiply by 100 here. So you'll get kind of like a decimal. But you basically take the moles, whatever you're interested in, divided by the total moles, gives you that mole fraction in this particular case. And we did, I think, all these when we did the example the last time. All right, any question on some of those concentration units? Obviously, molarity, you should know, hopefully, still moles per liter. Any questions on any of those there? All right. So then let's talk about colligative properties, where we'll use some of these concentration units for solutions. So colligative properties are basically based on the number of particles that are in the solution. So having particles in a solution will have an effect on certain properties of that particular solution, things like boiling points, things like freezing points, things like vapor pressure, and it's all really determined by how many particles there are floating around in there. So when we talk about these things, for example, if we had just, say, a solvent by itself, like water, there's pretty much nothing in there but water molecules, which means when you go to heat it, say at its boiling point, you could start to heat it and it will eventually gain enough pressure that these water molecules can pretty much freely escape the solution and really start to boil. Now, if you take water and you dissolve, say, some sodium chloride in there, so you put some sodium chloride into here. So in addition to your water molecules, you also will now have floating around in there some sodium ions, chloride ions floating around. As you can even see from my drawing here, it's getting a little crowded in there. Yeah, so, and the pool is getting a little bit crowded. So much like a swimming pool, right, with a lot of people in there, it takes a little bit longer to kind of weave yourself out of it, right? Same idea happens here because of the solute that's been dissolved in there. It takes a little bit longer for these water molecules to kind of work their way around everybody so that they can kind of escape the solution. The result of that, as we'll see in just a second, is it actually will increase the boiling point of water, for example. So that solution will boil at a higher temperature than just water by itself because of the presence of those extra solute particles that are floating around in the solution. It also can have an effect on the freezing point as well. It will actually lower the freezing point of the solution, having that stuff in there. And it'll also have an effect on the vapor pressure because, again, if it's harder for things to get out of solution, you're going to have less gas molecules above the liquid and you'll have a lower vapor pressure as well. So the idea of colligative properties is as you kind of throw more junk into the pool, if these things get in the way of the natural process of things freezing, of things boiling, and things being able to escape the solvent if it was there by itself. Any questions on that there? So the first type of colligative property we're going to talk about is what is known as vapor pressure lowering. So much like the name implies there, the vapor pressure of the solution will be lower than the vapor pressure of the solvent, for example, by itself. So the vapor pressure of substance depends on the nature of the substance and its temperature. As you add more solute to the substance, its vapor pressure is lowered, again, because it's really harder for those guys to start to evaporate. So the idea here is with nothing in the way, we're just going to get everybody to freely flow out above and get a lot of evaporation. And we'll have sort of a vapor pressure. Again, with stuff dissolved in there all over, it's going to take a little bit longer for these guys to kind of work their way through. We're going to get less sort of gas molecules above the liquid portion. That's going to result in really our vapor pressure coming down. So there is a formula here, which is PZ is equal to XZ times P naught Z. That's a lot of Z's, I suppose. PZ is the vapor pressure of the component in the solution. The naught here is the PZ of the pure substance. So this is our pure substance. This is really like our solution. And this is our mole fraction that we just talked about there of our component. So once again, the moles of what you're interested in divided by the total moles in this case. The vapor pressure lowering is defined as really the vapor pressure of the pure substance minus the vapor pressure of the solution. It is lowering, which means the solution will always have a lower vapor pressure. So we take the solution, the solvent minus the solution, and that'll give us a change in the vapor pressure here. So let's take a look at one here. The vapor pressure of ethyl alcohol is 66.5 torr. Calculate the vapor pressure of ethyl alcohol in a solution of 0.2 moles of glucose is dissolved in 1.2. Okay, so let's take a look. So we're going to use our vapor pressure formula. So we want the vapor pressure of the alcohol would be the mole fraction of the alcohol times the vapor pressure of really the alcohol that's pure. So we do need to figure out our mole fraction. So our total moles in this case would be our 0.2 plus our 1.25. And that gives us our total moles of 1.45. That means that the mole fraction of our alcohol will be our 1.25 moles, which is the moles of the alcohol divided by 1.45 moles, which is our total moles. Once again, we're not going to multiply by 100. So we're going to take the decimal of that, and that's going to give us basically 86%, 0.862. We have our vapor pressure of our ethyl alcohol, and in this case, you don't have to convert it to anything. You can leave it in torr. So the vapor pressure of our alcohol solution here is going to be 0.862 times our 66.5 torr, basically about 86% of that there. We'll get you 66.5. Looks like a 57.3 torr would be our vapor pressure of the solution that has the glucose in it. So glucose is a non-ionic solute, right? It is molecular, but the glucose gets in the way of it, which means less of these alcohol molecules can escape the solution and become vapor above it. And what we see is it goes from 66.5 down to 57.3. So the vapor pressure is lower because of the presence of the glucose. Less of them are escaping, and we have less pressure above the liquid. Any question on vapor pressure lowering here? All right, another sort of colligative property is the answer. There you go. Hopefully they got the same number. That would be good. Good. Is freezing point depression. So as I mentioned before, the presence of these solute molecules will get in away in the process of guys coming together to freeze, because there's lots of other things sort of in the way as it comes together. So actually the effect that it will have is it's a depression, which means the freezing point temperature will actually be lower than it is in the pure solvent. So the presence of that will allow it to lower the freezing point. And we do have a freezing point depression equation. This is the change in the freezing point temperature is equal to Kf times M. So this is our change in freezing point temperature. Kf is the freezing point constant, and it is a value that you would look up on a table, and it is based on the solvent. So very often people, when they go do these problems, go, I cannot find sodium chloride on the table. And that is because if you had a sodium chloride solution, the solvent would most likely be water. Yeah. So it is the solvent that's on the table and not the actual solution. So whatever was used as a solvent. And by the way, on these problems, water is not always the solvent. A lot of times it is, but it's not always the solvent. So you want to make sure that you do look up the right solvent. M is molality that we just talked about again, and that is our moles per kilogram of solvent. So this is the change in freezing point temperature. When you calculate the change in freezing point temperature, because the solution will actually freeze at a lower temperature than the solvent, This is a very important part of that calculation, which is the change in the freezing point temperature is the temperature of the pure solvent, because it'll actually be a larger temperature or a higher temperature than the temperature of the solution. And you do want to do this one as solvent minus solution gives you the change in freezing point temperature, and that will give you the proper minus or positive sign. So you want to always do, in this case, solvent minus solution with freezing point. And we'll see some examples of what that sort of entails in just a second. Any questions on that there? Now, it also does affect the other end of the spectrum, which is the boiling point aspect of it. And for example, freezing point here, like you put rock salt, right? You can make ice cream, right? And it gets really cold because of that sodium chloride that's in there. Boiling point was actually affected in the opposite direction. It will actually increase the temperature at which that solvent will boil. So it's boiling point elevation. So the presence of that solute particles will cause the boiling point to increase. This is basically what antifreeze does in your car, right? It actually does both things. It lowers the freezing point in case you live in really cold temperature, and also increases the boiling point in your car of all your water and stuff like that. So if you live in a very hot area, like maybe Arizona or maybe here some days, you don't overboil, right? So that's the purpose of the antifreeze, is to actually lower the freezing point so everything doesn't freeze in cold temperatures, raise it in hot temperatures so that it does not overboil. It has a very similar equation, which is the change in the boiling point temperature is equal to our boiling point constant times our molality. So once again, that is not the actual boiling point temperature, but it's the change in boiling point temperature. This is our boiling point constant, which once again is based off of the solvent. And this again is our molality, which is our moles per kilogram. This one is different because this is boiling point elevation. The solution will boil at a higher temperature than the solvent. So it'll be a larger number than the solvent. So in this one, the change in the boiling point temperature is the temperature of the solution minus the solvent. So this one is opposite of the previous one, where we take solvent minus the solution. This is going to be solution minus solvent. By the way, the temperature in all these usually could be left in degrees Celsius because the KB and KF there are usually in units of Celsius. So a lot of times you're okay. You don't have to do any type of Kelvin conversion with these type of formulas. Any questions on that there? All right, so let's take a look here. This is a table where you could look up these values. You obviously have one in your book that's similar. A couple of notes. Here's water. So this is very commonly used. The normal freezing point is 0 degrees Celsius, right, for water, and 100 degrees Celsius. And it's 1.86 for our freezing point constant, 0.512 for our boiling point. It's also important to remember that if it is not water, two things will change. The actual KF value and KB values will be different than what you find for water. And also the freezing point temperature and boiling point temperatures are different for different substances. So you don't want to use 100 and 0 in these calculations if it's not water, right? So you want to use the proper boiling point and freezing point for that, along with obviously the proper temperature. Once again, this table is based off the solvent, not the solution. So whatever was used as the solvent is what you want to look up in this type of table. So let's take a look at this one here. What is the freezing point of a 1.7 molal ethylene glycol solution of C2H6O2? The KF for water freezing point equation. So our change in our freezing point temperature is our KF times our molality. In this particular case, they actually gave us the molality, but in some cases you do need to calculate it yourself. So we do have the molality, which is 1.7 moles per kilogram. We do have our KF here for water, and once again, we look it up because it is a aqueous solution, right? So aqueous is the key word there for water, right? Is going to be our solvent in this case. This is a non-ionic solute that's in there, so it's going to stay together basically as one unit as it goes in for a swim. So really in this case, we could just plug it in. Our change in freezing point temperature would be our Kf, which is 1.86 degrees Celsius times molality. And again, why you can leave the temperature there in Celsius when it's all said and done, times our molality, which was calculated for us, which is moles per kilogram. And that basically cancels. And that gives us 1.86 times 1.7. And that's going to give us a 3.2 degrees Celsius. Is that the answer? That is not the answer. That is, again, only the change in freezing point temperature. And it would not make sense because this should be a freezing point depression, which means our temperature should be lower than what we started with. The normal freezing point temperature for water is 0 degrees Celsius. So if this guy froze at 3.2 degrees, that's not good, right? So that's not going the right way. So this is where the change in the freezing point temperature relationship is important. That is going to be our temperature of our pure solvent minus the temperature of our solution. So what we just calculated, again, is the change in freezing point temperature, which means it's 3.2 degrees Celsius. Our normal freezing point of our solvent is 0 degrees Celsius minus the temperature of our solution. That means essentially we need to take the negative to the other side, right? And that would tell us that our solution would actually freeze at minus 3.2 degrees Celsius. And that does make sense, as that obviously is lower than 0 degrees Celsius. So that's why that little change in temperature of freezing or change in temperature of boiling is important, so that you end up with the correct sign, or in some cases, subtract or add appropriately and not do the wrong math question on that particular one there. So once again, the presence of this ethylene glycol is really preventing these guys, the water molecules, from being able to kind of come together cleanly. And it takes a little bit more removal of energy to get everybody to kind of slow down. And that's going to be 3.2 degree difference from where it normally would freeze. Any questions? All right, let's try another one there. Calculate the molar mass of a compound if a solution of 12 grams is dissolved in 80 grams of water, and it freezes at minus 1.94 degrees Celsius. So give it a try here for a couple minutes there. We're looking for grams per mole, right, which is the molar mass. Okay, so let's take a look. So we're looking for grams per mole. So we obviously have our solute here, which is dissolved, and our solvent, which is water. And obviously that is why we looked up the Kf there for water, which is our solvent in this case. We do have the freezing point temperature of this solution, which is minus 1.94. Since it is water, the normal freezing point temperature of water is 0 degrees Celsius. So we're looking for grams per mole. We actually have the grams part given to us, which is right there. So that is the grams part. So really what we're looking for to be able to get to the moles part is we want to kind of use the freezing point information to help us do that. So if we think about our freezing point equation, it is our Kf times our molality. So we obviously can have the Kf that we could look up. We were able to figure out the change in freezing point temperature. That means that we can use that information to get to the molality, which is good because that is moles of solute divided by kilograms of solvent. And that's okay because I do have the grams here of solvent that I could get to the kilograms to get me to eventually the moles of the solute, which is really the bottom part of the solution that I need, or the calculation that I need. So we're going to use that freezing point information to kind of use the molality to get to the moles part of it. Any questions on that pathway there? We do have to do actually something with this. This is not the change in freezing point temperature of that solution. That is actually the freezing point temperature, right? Which is minus 1.94 degrees Celsius. So again, if we go back to our change in freezing point temperature, that's the temperature of the solvent minus the temperature of the solution. That means that the change in freezing point temperature would be 0 degrees Celsius, which is where water normally freezes, minus a minus 1.94 degrees Celsius. That is how we get rid of the negative that we really don't want in this case, and that's where that comes from. Yeah. Any questions on that? That 1.94 is actually the change in the freezing point temperature and really what you want to use here in this formula. So you don't get any negative numbers or anything like that. So the change in the freezing point temperature is equal to Kf times M, which means M would equal the change in the freezing point temperature divided by the Kf. So putting our numbers in, 1.94 degrees Celsius divided by 1.86 degrees Celsius molality. The degrees Celsius will cancel when we divide. We'll take 1.94 divided by 1.86. Going to give us a 1.04 as our molality here. Any questions up to that point? So that is what we're going to use to get the moles. We do need to do a conversion of our solvent as from grams to kilograms. So the mass of our solvent, which is our water, is 80 grams, and there are 1,000 grams in a kilogram. And that will get us 0.08 kilograms of water. Now, using our molality, which is moles per kilogram, and we times it by our 0.080 kilograms. Kilograms will cancel, and that will get us here times 0.08, looks like 0.0834 moles. That is the bottom part here of what we need to calculate the molar mass. Any questions on that move right there? That means all that's left is to divide. So let's do that. We're going to take our molar mass will equal the grams, which was given to us as 12 grams, divided by our moles, 0.0834. And if we do that, 12 divided by 0.0834, looks like 144 grams per mole in this case would be our molar mass. So here we're using really the freezing point information to allow us to really to get to the moles. And obviously the grams were given us to calculate something like molar mass. So you could use this information as you see here in this problem to calculate something like molar mass, in addition to just straight calculating out freezing point temperatures or boiling point temperatures. Any questions on any of those steps there? Yeah. Here it is in super slow motion again, I think. There you go. All right, so why don't you try this one? How many grams of ethylene glycol must be added to give a solution that boils at 105 degrees? Let me get the K. There it is. There's the KB for it, 0.512 degrees Celsius. And the molar mass of our guy there is 6207. So how many grams of ethylene glycol must be added to 1 kilogram of water to give a solution that actually boils at 105 degrees Celsius? To see what you come up with here. Okay, so let's take a look. So in this case, it's actually boiling point. So very similar equation. Our change in boiling point temperature would be our KB times our molality. Once again, in this case, we do have the temperature at which the solution boils, which means we can't get to the change in boiling point temperature. This obviously is in water, which is our solvent, which is why we would look up, obviously, this value there on the table. And that means we do have KB. So once again here, we can solve for molality, which is our moles per kilogram. And that's good because we do have the kilograms of solvent, which means we can eventually, just like with the freezing point information, we could get to the moles of the solute, which is ultimately kind of what we're looking for, which is basically how many grams of it. So we could go from moles to grams using the molar mass at that point. So here again, we're going to use our boiling point information to help us do that. The temperature of the solution boils at 105 degrees. We do not want to put that into here because that again is not the change in boiling point temperature, but that is actually where the solution actually boils. So this is where that relationship of the change in the boiling point temperature is the temperature of the solution minus the temperature of the solvent, which is reverse of the freezing point. And that means that the change in the boiling point temperature would be temperature of the solution, which is 105 degrees Celsius, minus our solvent where it normally boils, which is 100 degrees Celsius, which means the change in boiling point temperature is actually 5 degrees and not 105 degrees. Yes. So again, that's why it's really important to think about that change versus the actual temperature where it boils or freezes. Any questions on that there? Now that we do have that, we have what we need to solve for M, which is the change in the boiling point temperature divided by the KB. That is going to be 5 degrees Celsius divided by 0.512 degrees Celsius times molality, or divided by molality. 5 divided by 0.512 gives us a 9.77 moles per kilogram, our molality. This can then be times by the volume or the mass of our solvent, which in this case is already in kilograms. So that makes it pretty easy. And it's also 1 kilogram. So that works out pretty good of our solvent, which is water. That means that we will end up with 9.77 moles of our solute, which is this guy right here. That's our solute right there. So what's left now is to use the molar mass from the periodic table, but they were nice enough to give it to you, so I guess we don't have to calculate it, which is good. 9.77 moles of our C, whatever that is, 2H6O2. And we're going to use the molar mass. And again, if it was not given to you, obviously you would go to the periodic table to calculate it. The moles will cancel, and we'll take that and times it by 6207. Gonna get us like a 607 grams, and probably want about 2 significant figures since that's kind of the only number that's small. So maybe about 610 grams of our solute here, our C2H6O2 in this case. Yeah. Any questions on that one there? So it works very similar to freezing point. And again, here we could solve for something different as well. In addition to molar mass, we could also again figure out how much grams of that solute you need to dissolve in there as well, using, in this case, the boiling point temperature. So again, it's really important to make sure that you do stick the correct numbers in. I can't tell you how many people will roll with like maybe 105 on that. Again, you want to make sure that that is the change in either freezing point temperature or boiling point temperature. Any questions on that? All right, here. Let's try one more here. What is the boiling point of a solution made by dissolving 1 gram of glycerin in 54.0 grams of water? The KB 0.512, carbon 12.01, hydrogen 1.008, and oxygen 16. See what you come up with here. We're looking for, in this case, what is the boiling point temperature of this solution here. Okay, so let's take a look. We're looking for the boiling point temperature here of the solution. So again, we're going to use our boiling point equation there, our KB and our M. And we do have the Kb given to us, which is water in this case, as that is our solvent. And we are going to solve for our boiling point. So we have that. We do need the molality. So the molality, again, would be moles per kilogram of solvent. So the moles here of our C3H8O3, when we add all that together to get to the molar mass, looks like it is something like 9209 grams per mole. We do have how many grams of it that we're using. So 1 gram divided by our molar mass from the periodic table, 9209 grams per mole, will give us 1 divided by that. 0.0109 moles of our glycerin. And we want to divide it by kilograms of our solvent, in this case, which is water. We do have to, again, convert our grams of water into kilograms. So 1,000 grams is a kilogram, or move the decimal. We'll do that for you. So we're going to take that and divide it by our kilograms of solvent in this case, and that will get us 0.0109 divided by 0.054 gets us a 0.202 molality. So our change in boiling point temperature would be 0.512 times our molality of 0.202. Let's make sure I have the right number there. Feels a little bit off there. Divided by 0.054. Yep, okay. And that will be our molality here. So that's going to give us 0.512 times 0.202. That's going to give us 0.10 degrees Celsius. That, once again, is not the answer. That is the change in the boiling point temperature. So again, using the change in the boiling point temperature is the temperature of the solution minus the temperature of the solvent. In this case, 0.10 degrees Celsius equals the temperature of the solution minus our solvent, which is water, normally boils at 100 degrees Celsius. That means we actually need to add the 100 degrees to the other side, and that gives us a whopping increase in temperature of about 0.10 degrees Celsius as our boiling point. So 100.1 degrees Celsius would be our normal boiling point, or the boiling point of this solution here. Any questions on that calculation? Yeah.
Following the sig figs, like how we do it. I mean, would you leave it like that?
Yeah, so technically speaking, here we should have 3 sig figs, right? And here we also have 3 sig figs, which means we should end up with 3 significant figures here. We would take basically 3 significant figures here, which technically would take us to here. It really would depend on this last part, how you use the 100, right? So in this case, you could use 100, 100.0, or 100.00. So it would really be dependent on this one. Technically speaking, the way I wrote it here, you should go to no decimal places, really, in this case. So we'll just pretend I had 2 decimal places there. So we will be okay in that case. But it really would depend on that last step. So up to that point, it was 3 significant figures. The last step there, you're basically adding. So you would go at decimal places, and I kind of left off the couple of zeros there for the normal boiling point. So it would really be dependent on what number you use for that particular one. Other questions on that? Here, we probably wouldn't want to take it strictly on the significant figures if you did use 100 like I did originally, because then it would just be the same answer, right? So here it's kind of important to get a couple of digits past it. Other questions? Questions on boiling point, freezing points? All right. Another sort of property that is a colligative property is osmotic pressure. And osmotic pressure is basically the pressure that's exerted to stop the flow of solvent molecules from one side of a membrane to another. So if you had a tube that had a semi-permeable membrane in between, and you had, say, salt water on one side of it and just plain old water on the other side. The process of osmosis means that solvent molecules will go from the lower concentration to a higher concentration. So they will flow from kind of a lower concentration to a higher concentration in an effort to essentially dilute down the other side, basically, because there's kind of unequal balance on each side. Osmotic pressure means that in this case, our water molecules will flow to the saltwater side because it's more concentrated, because it simply has stuff dissolved in it, right? So if you have more stuff dissolved in it, the more concentrated something's going to be. And it will continue to flow until it reaches pretty much atmospheric pressure pushing back down on it. And that is what is known as the osmotic pressure. At that point, it will stop the flow of more water molecules to the other side because it hits that osmotic pressure. Reverse osmosis, which is a process sometimes used to purify things, is when you apply a pressure greater than the osmotic pressure. And what that does is it sends all the water molecules back the other way. You have some good filters in the middle there to catch everything you don't want to go across. And you can kind of purify it through the process of reverse osmosis. So we could calculate osmotic pressure by using this really great equation here, which frankly is PV equals nRT. That is the ideal gas law with some fancy symbols, like that is the osmotic pressure, the little pi symbol there. This is, if you solve for the pressure, like we did before, nRT over V. N and V is moles per liter, right? And that is how come it reduces to the molarity times R times T. But ultimately, to calculate the osmotic pressure, it's pretty much an ideal gas law type problem, is what we'll use it for and how you can use it. So the more solute that you have dissolved in a solution, the higher the osmotic pressure is. The less solute, the less osmotic pressure. Pure water has no osmotic pressure because it has nothing dissolved in it. It's just water molecules basically there. Any questions on that there? So we could do some osmotic pressure sort of calculations, very similar to what we did in the gas chapter. And we could calculate the molar mass here, which is grams per mole. And if we just think about really our osmotic pressure, and I'm just going to make it the ideal gas law because frankly, it is the ideal gas law. So why not just call it what it is? What is the molar mass here? This is pretty much the same problem that we did when we talked about calculating molar mass. And we did density of gases and molar masses of gases. And solve for our moles here. And that's because we do have the pressure, we do have the volume, we do have the temperature, and obviously we do have R, which is our gas. That's going to give us our N, which is the moles part. Here is our grams part, but we do need to do a conversion as it's in milligrams, but we do have the grams part. So N here would be PV divided by RT. And we do have to do some conversions. So you do need to remember it's still the ideal gas law. So you got to get everybody in the right units. So we'll take our volume here of 10 milliliters and convert it into liters. So that's 1,000 milliliters is a liter, 0.01 liters. We do need to convert our pressure into atmospheres. So we'll divide it by 760. That's going to give us 0.00322 atmospheres. And like normal here, we do need to convert our temperature into Kelvin. So that's going to give us 298 Kelvin. So at that point, we have everything that we need to use the ideal gas law here. So the moles will be our pressure, our volume, divided by 0.08206. And our temperature there of 298. So here we're really just kind of using ideal gas like we have done previously to figure out our moles. And if we do that there, get it, oops, divided by 298. Going to give us moles of 1.32 times 10 to the minus 6. So now that we have the moles part from our ideal gas law, we need to convert our milligrams into grams. So 5.87 milligrams, that's the same as milliliters and liters. So that's 1,000 milligrams is a gram. And we're going to take that 5.87 divided by 1,000. Going to get us 5.87 times 10 to the minus 3 grams. Now we can just divide the two. So our molar mass will be 5.87 times 10 to the minus 3 grams divided by 1.32 times 10 to the minus 6 moles. And that gives us 5.87 to the minus 3 divided by 1.32 to the minus 6. And that's going to get us here 4.45 times 10 to the 3 grams per mole. That's like 40 something, 4,400 grams per mole, which would be our molar mass here of our protein. So it's a protein, so probably is pretty big. So it has a pretty large molar mass. Question on that calculation there. Again, pretty similar to, not similar, it's pretty much identical to what we did in the gas chapter. Any questions on that? So let's try one more here then. Why don't you try this one? What is the molar mass of a lysozyme? That is 0.075 grams per 100 milliliters. Gives an osmotic pressure of 1.32 times 10 to the minus 3 atmospheres at 25. Okay, so once again, in this one, we are looking for really the molar mass, and we do have the grams given to us, and this actually in grams, so we're good to go on that. Once again, here we're going to use really our osmotic pressure formula, aka the ideal gas law here, to get to the moles part of it. Here we do have 100 milliliters, which once again, we do need to convert into liters, so we'll divide it by 1,000, and that will give us 0.1 liters. Our pressure here is actually in atmospheres, so that's good. And we'll add 273 to get to our Kelvin. So once again, here we'll solve for N, which is PV over RT. And that's going to give us 1.32 times 10 to the minus 3. Atmospheres, our volume, 0.1 liters divided by our R, and our T of 298 Kelvin, and that will get us here 1.32 to the minus 3 times 0.1 divided by 0.08206 divided by 298 gets us 5.398 times 10 to the minus 6 moles. Once again, we're already given it in grams, so all that's left to do is divide those two and see what we come up with here. And that gets us 0.0750 divided by our answer there. Going to get us something like 1.39 times 10 to the 4 grams per mole. And this is also a pretty big molecule, so it has a pretty big molar mass in this case. Yeah. Any questions on that? Again, this is pretty much identical to what we did in the gas chapter. Yeah. Any questions on osmotic pressure here? So if you're comparing solutions that want to know which one should have, again, the larger or greater osmotic pressure, again, based on the number of particles that are in that solution, that would definitely be the one that has the greater osmotic pressure. So up until this point, when we're doing our boiling point elevation, our freezing point depression, our vapor pressure lowering, we only kind of dealt with one type of solute that was in there, like glycerin and antifreeze and all that. And these were really non-ionic solutes. So when we have non-ionic solutes, like the ones we did in these previous examples, when it goes for a swim, pretty much one molecule will produce basically one particle. And that's important because really colligative properties are based on the number of particles that are in that solution. So more particles, more sort of interaction. So when we take an ionic solute, like say something like sodium chloride, when we put something like sodium chloride into a solution, and it goes for a swim, we get a sodium ion and a chloride ion. We actually get two particles for every one that we toss in there. And if we put something, say, like calcium chloride into a solution, we get a calcium ion and two chloride ions. That's actually like a 1 to 3 type of situation, right? For every one of those that you toss in there, you get 3 particles. So since colligative properties are based on the amount of particles that are in there, having multiple particles coming into the solution in terms of an ionic compound will have an effect on things like the boiling point and the freezing point and the vapor pressure as well. So that is what is known as the von Hoft factor. The von Hoft factor is abbreviated with an I. And the I basically stands for how many particles you kind of have in there floating. So in the case of something like what we dealt before, this non-ionic I would equal 1, which is why we didn't really take it into account in any of our formulas, like our change in boiling point, or our change in freezing point, for example, or even our vapor pressure, because technically it's 1, so we don't do it, so we don't have to multiply by 1. But when we do have an ionic solid that's going in, or solute that's going in there, we do have to take it into account. So in the case of something like sodium chloride, I would equal 2 because you get 2 particles for every one that you toss in there. Something like calcium chloride, I would equal 3 in this case. And you can actually figure out the von Hoft factor by really just how many particles you get. So how does that affect it? Well, we actually will insert this von Hoft factor into our equation, and we will take I times KBm and I times KFm, and we will insert it into our equation. So how does this make a difference? Let's just take a pretty straightforward example. Let's just say for each of these solutions, we had a 2.5 molar solution of each of these guys here. So if we did our non-ionic guy, and we're going to do the freezing point here. So we'll do the freezing point where the KF is 1.86 degrees Celsius and molality, as we will use water. We would calculate our change in freezing point temperature as 1.86 times our 2.5. So this gives us 2.5 times our 1.86, which is going to give us 4.65 as degrees Celsius as our change in our freezing point temperature. Now, if we did this exact same calculation for our sodium chloride, where our I was equal to 2, in this case, our change in our freezing point temperature would be 2 times our 1.86 times our 2.5 as I squeeze it in the little spot right there. And we will end up with 1.86 times 2 times 2.5 gives us a change in freezing point temperature of 9.3 degrees Celsius. So you can see by having the more particles in there, we're actually going to have the freezing point come down a lot more because there's a lot more particles in the way. And if we did it for our calcium chloride in this case, where I would equal 3, our change in our freezing point temperature will be 3 times our 1.86 times our 2.5 m. And we will end up with something like 13.95 degrees Celsius as the change in freezing point temperature, an even greater decrease because there's a lot more particles basically in that solution at that point. So when you're dealing with an ionic solute that's being dissolved in a solution and you're dealing with colligative properties like freezing point depression, boiling point elevation, vapor pressure lowering, you do have to take it into account. And as you can see, it can have a pretty drastic effect on the degrees that change in terms of their temperature. Question on that there. So if we were going to look at a table here. The expected one, which can be done from the formula, is also very close to what you get in terms of the experimental value. Yeah, you could also use it for the osmotic pressure. Mainly, you would use it for probably the vapor pressure lowering, the freezing point, and the boiling point. You don't necessarily have to include it in that particular one, usually in most cases, but those other three are typically where you would kind of insert that into. Yeah. Other questions? So expected here is pretty much based on the formula. In most cases, when you're doing calculations, that's pretty much what you could do. So if you had a potassium sulfate, when that guy breaks apart, you get 2 potassiums and a sulfate. And again, that is how we get the I is equal to 3. As you can see, it's about 2.6 experimentally, 2.7. So the measured value of these experimentally is a little bit off from what you would predict, but in a calculation sense, you could just do it based off the formula and you can figure out the I. So let's finish up here with what is the measured von Hoft factor if 0.05 mole calcium. Okay, so let's take a look at this. So obviously we're dealing with freezing point. So we're going to have our freezing point equation. We do need to include the von Hoft factor here of I times our Kf times our molality. We need to include the I because we have calcium chloride, which is again is ionic. We also know that we will use water because it's an ionic compound, which means water is definitely the solvent of choice. And that also means that our normal freezing point is 0 degrees Celsius for water. Once again here, this has a freezing point temperature of minus 0.27. We need to really get rid of the minus like before, the negative. So our change in freezing point temperature is again our temperature of our solvent, which will be a larger number, minus the temperature of the solution. So our change in freezing point temperature would be 0 degrees Celsius minus, once again, our minus 0.27 degrees Celsius. So that again is how we get rid of the negative that we should not have in this problem. And that will give us our change in freezing point temperature of 0.27. So 0.27 degrees Celsius is equal to I, which is what we're looking for actually in this problem, times our Kf, which is 1.86 degrees Celsius times molality. And in this case, they actually gave us the molality of 0.05. So the molality will cancel. That's going to leave us degrees Celsius. So we'll have, if we clean up the left-hand side, 1.86 times 0.05. And that gives us 0.27 degrees Celsius equals I. 9.3 times 10 to the minus 2. Clearly, I got my calculator and scientific notation at this point. We're going to then divide this to the other side. So that's going to be a 0.2 divided by that. And that will give us a I of about 2.9 in this case, experimentally found. Question on that one. That is very close to what we would expect to predict based off of the formula of calcium chloride as we did earlier. That is 3 particles, which means we would predict I should be 3 in this case. And this is why, again, in most cases, if you're doing problems, you could just go off of the formula. It's going to be very, very close to the predicted value. So that's really important to make sure that you do include in any ionic solute that von Hoft factor in your calculations. Otherwise, obviously, as you can see from the previous ones, your final temperatures are going to be significantly off because you didn't take into account the particles that are present. Any questions on that there? All right, well, I think that's a good place to stop.